Ray, one of our mentors here at SharpestMinds. So Ray Phan is a seasoned veteran in computer vision and deep learning. He has worked in multiple industries in both the SF Bay Area and his hometown in Toronto, Canada, in robotics, self-driving cars, 3D reconstruction, consumer 360-degree cameras, medical devices, and augmented reality. He currently works at Magic Leap, where he works on the world reconstruction team that's within the Perception organization, where he researches, designs, and builds pipelines for reconstructing the real world using various sensors. He holds a PhD in electrical engineering, as well as being a licensed practicing engineer and a senior member with the IEEE. Finally, Ray is also a Sharpest Minds mentor, guiding mentees for pursuing careers in computer vision and deep learning. So before I hand the floor off to Ray, just gonna talk about logistics here. So you guys can ask questions in the chat or use the raise hand function. And after Ray's presentation, we will be going through your questions. So with that, thank you so much for being here. Thank you, Ray. And yeah, handing the floor off to you.
Thanks, Amber, for the wonderful introduction. Hi, my name is Ray, Principal Software Engineer at Magic Leap, as well as a mentor with the Sharpest Minds platform. So my talk today is about weekly supervised object detection. So as you hopefully are aware in practice, when we train an object detection system, you usually have a bounding box of where the object is located, as well as a class of where, identifying what that object is. So weekly supervised is the case where we want to achieve the same performance, but having less information that is available to us. So that's the problem that I want to address. Can we, train an accurate object detection system with having less information than what is typically seen, when you're training stuff in industry? So just some preliminaries before we get started. I want to differentiate between what is weak versus strong supervision. Strong supervision is what you're probably aware of. You got a set of labeled training examples and you want to train some, predictive model to classify a set of inputs. And then I want to talk briefly about the different kinds of object detection categories, just to make sure that we're grounded and we know, what exactly we want to focus on. And then I want to talk about, the thing that I'm very passionate about, which is weekly supervised object detection, or WSOD for short. And then I want to dive into the seminal work by Bill and Videlli from the Computer Vision and Pattern Recognition Conference in 2016. This is where it all got started. And then just a brief overview of just talking about a couple of research papers that extended this work, just to get you started in case if you want to know more. And then I'll conclude this talk. So this is a graphic that I really enjoy talking about because it really puts into perspective the challenges in object detection. So we have varying degrees of information that is available to a person who wants to train an object detection system or image classification system. So we have on the extreme left, let's say the goal here was to identify what objects are in the image. So at the most extreme case, if you want to just tell you whether or not there's a motorbike or a person, the average labeler will take about a second per class. So in this case, there's two classes here that we want to identify, motorbike and person. It takes roughly 2 seconds to say that, okay, there's two of those objects are definitely in this image. And then you get to the more extreme, get a little more extreme where let's, click on a couple of points that differentiate between a motorbike and a person. So if we have just a couple of points for each object, and if we wanted to train some sort of object detection system that uses this information, just clicking on a couple of points takes roughly, maybe 2.5 seconds per instance. Per object. And then you get to the more canonical cases, what we're used to, especially if you take a look at companies that offer kind of labeling services or services that'll take your data and label things for you. This is what we typically expect when we're training an object detection system, where you take a bounding box, you draw a kind of a rough surrounding of where this object is in the image, and then you also tag what that object contains inside the bounding box. So you've got one box for the bike and another box for a person, and that takes roughly 10 seconds per object. So here we're starting to get to 20 seconds for instance, and then you see that the amount of time taken takes much longer the more information you want. And finally, the most extreme case, this is what's known as semantic segmentation, where you classify each pixel in the image. So what you do is you take a brush or some sort of a stylus, and you're actually styling or you're identifying every single pixel in this image. And to do this, requires roughly 70 to 90 seconds per image, and that can take a very, very long time. And this is especially useful for in the medical industry. You want to identify tumor pixels or abnormalities where you need exact classification of each voxel to provide some diagnosis. So going from left to right, the more information you need or the more accurate that you want your system to be, the more time it's going to take for you to label the actual data. So what we want to focus on is weak labels, or labels that have less information than typical, but can we still train an object detection system to be just as accurate as systems that have much more information than usually given. So this graph also I love to present. So what we have here is just a graph where the source is what we have available during training time, and the target is what we want to predict at test time. So standard supervision just is pretty much a slope of 1, where for each training example you have, if we have an image label, we also want to predict an image label as well. So the inputs that you take in are also the inputs at test time that you're expecting. So just standard supervision is anything along this axis. So if you have a bounding box, you output a bounding box. You have a pixel label, you get a pixel label. So that's pretty kind of standard training. And then you have weak supervision, where we're talking about this area of space where you have less information than required, but you want to predict more things about the image at test time. So this talk is specifically, where this starts, where I just have a label that tells me whether or not there's something in the image that contains either a motorcycle or or a bike or a person, and the output is draw me a bounding box where this person is or where the bike is. So I have less information available, but can I still predict with high fidelity much more information than I was actually given? So that's what weak supervision is. And then strong supervision is the other side of the spectrum, where it's not really seen as much, mainly because you can consider it as kind of a waste of resources. Why would you, provide so much information and then provide just, something small about it? So that's not typically seen, but it has been done before, where you get more information at the training time, but then at test time, you provide, just less information than what you actually need. So that, is sometimes done, especially if you have a lot more training data that you acquired previously, and you want to train a system that doesn't, need to output as much information as you need. So let me just talk about some object detection categories very quickly. So there's 4 particular object detection categories, even though you probably have just seen one. So the first one is what we call supervised learning. So that's the typical kind of use case or systems that we've seen in practice, where you have a bounding box that delineates the object of interest, as well as a tag or label for that same bounding box. So we have a bounding box and we have a label, and these pairs together are used to train some object detection systems. So then at test time, you input an image and it produces a bounding box of where things are, as well as a class of what that bounding box belongs to. So that's supervised learning. We have a one-on-one correspondence. So you have a bounding box and label at training time, and then at test time, you also identify objects as well as classes that each box belongs to. And then you have weakly supervised learning, where we just want to identify whether or not an object exists in the image. So there's no bounding boxes at all. So at training time, we'll say that, yes, we see a horse, we see a person. And at test time, yes, is there a horse or is there a person? So you're testing for the existence of an object, not necessarily where they're located in the image, but whether or not they exist somewhere in the image. It doesn't matter where, but as long as they exist somewhere, that's weakly supervised learning. Or it's a case of multiple instance learning if you attended my talk previously about a couple months ago. And then you have semi-supervised learning, which is on the bottom right here, where you have some images that contain both bounding boxes and labels, and other images that contain absolutely no information at all. So this is a typical case where you have a very small set of labeled data, and if you're doing some web crawling or web scraping and you're grabbing some other data, which potentially can be unlabeled, can you still train an object detection system where you have a mixture of unlabeled data and labeled data, bounding boxes and labels? Can we train an object detection system that will work in spite of having missing data? And finally, this is another niche one that's actually seen much more frequently in the medical industries, where you have weakly semi-supervised learning, where you have a mixture of bounding boxes and labels, and that you have other images that just contain labels and no bounding boxes. So the mixture of those two, can we train a strong object detection system for there? So that's actually quite commonly seen in the medical industry specifically, where it's more fruitful to identify whether or not there's certain cancerous cells or certain tumors without having the radiologist, draw a bounding box, because there's a lot of images to go through, very high resolution, so it takes a lot of time to get that actual data. So it's much more fruitful to say, yes or no, and have that data and build that into a system rather than having to do it, for each image individually. So weakly supervised object detection is actually a mixture of multiple instance learning and weak supervision. So the ground truth, or the labeled data that you have, it only identifies whether or not you have an object that exists inside the image or not. It doesn't have any bounding boxes. You just identify whether or not there's a motorcycle or a person in that image, but you actually don't know where exactly inside that image the object is. Oopsie, what the? I gotta close this. Sorry. Let me just close this. Okay, sorry about that. Yep. So you actually don't know exactly where the object is located in the image. So those are what we call image level labels. So given just labels of where of whether or not there are objects in the image, can we find bounding boxes of where exactly these objects are located? So you're performing object classification, so deciding whether or not there are particular objects in the image, and localization, where exactly they are in the image, just using these image level labels. The appeal for this is that you can get a lot more data in a short amount of time. Instead of, if you just have image level labels, you can get those pretty quickly versus having to draw bounding boxes, which is a little more, I suppose, invasive of the labeler's time. And we still want to be able to achieve as accurate results as having an object detection system that was strongly supervised, where image and bounding box at train time, and we want to be able to predict image label and bounding box at test time. Yeah, and I just talked about that. So, getting data would obviously include less time required to get, the data to train. So the goal of WSOD, or multiple instance learning, is you have a set of proposed bounding boxes that you present to a training system, and the goal is an object that I'm interested in, does it exist in any of these bounding boxes? And if that answer is yes, if it exists in at least one of these bounding boxes, then sure, the answer is yes, and then no if none of these bounding boxes contain, the object that you're looking for. So if you remember that multiple instance learning talk, we had that concept of bags versus instances. So in this case, one bag is a single image, and instances are these bounding boxes that you propose to check to see if this object is inside any of these bounding boxes. So the goal is to train a classifier where, given these proposals or these bounding boxes, can we identify where, if an object exists in any of these proposals. So just some quick takeaways from multiple instance learning. We say an image is positive if you have at least one object of the particular category you're looking at that's present in the image. And we also say it's negative if there are no objects of interest of a particular category you're looking at, if they're not actually present. So we work with two predominant assumptions here. The first is we take a look at, in terms of classification. So when we build a classifier, when we build some sort of detection system, you are taking these bounding boxes and converting them into some latent space using some convolutional neural network or some sort of feature extractor. And for multiple instance learning, or WSOD, to work, there has to exist a set of features that can differentiate between positive images and negative images. So we don't see these features in negative images, but we do see these features in positive images. And if we want to look at it in terms of a detection side, these same features that you pulled from the feature extractor, they uniquely represent this particular object. So these features are not shared between other classes or other objects to distinguish them between each other. And that for objects that you take with your cell phone camera or or other cameras, there can be a difference in size, there can be a difference in viewpoint, there could be background clutter, there could be things that block the object's field of view from the camera, which are called occlusions. So those are things that we definitely have to deal with when it comes to WSOD as well. And on top of this, there's actually more issues to deal with because of a lack of information. I'll talk about this quickly. So when you're dealing with, WSOD, the point is, given an image, can we identify or localize, the object in the actual image? So there's a problem of part versus object. So let's say the problem here was to, I know that there are humans in this image, but can I train a system to actually localize where exactly these humans are? And given a lack of information, this can be challenging because, well, are you trying to identify what exactly is a human in this particular object? Is it the face that you take a look at? Is it the whole body? And there's, taking a look at the composition, like there's also the more than one human here. So do the collection of humans also factor into the training? Like you're providing, very little information to the detection system saying, yeah, this image represents a human. And then you're telling it to try to learn where exactly to find these humans. So with the lack of information comes challenges on deciding what exactly is the best representation of a human, the face, the parts of the body, the whole body, like it. So that ambiguity is very prevalent in kind of weakly supervised detection systems. And then you also have context too. Let's say the goal of this was to identify where exactly the train was in this image. So usually the trains, you see them on railways or rail tracks. You typically don't see them outside of rail tracks. So when you want to be able to localize whether, where the train system is, when you're extracting features, do you, what exactly is a train here? Like, do you take a look at just the train, or is it just the train and the rail? Also, usually trains are outside. So do you take the sky and the background into account when you're actually training the system? So trying to infer context with very little information also proves a challenge when you're training these kinds of systems. And then finally, you have multiple versus single objects, right? So let's say the challenge here was identify where the sheep are in this image. So with an image level label, are there sheep here? Definitely, yeah. The question is yes, but then how do you train it to isolate out, more than one possible sheep? So, what exactly is the definition here? Is it 2 sheep? Is it 3 sheep? They're usually outside. So do you consider the grass as well? Just the grass by itself. So there's also context in terms of, multiple single objects as well that prove to be a problem. So here's a typical kind of a WSOD pipeline. So it's an iterative process. You go back and forth. So the first is to initialize the system. So you create what are known as region proposals, or bounding boxes that are candidates that may contain the object of interest that you're looking at. And then using these proposals, you train a system that will use this bounding box information. And then you use the bounding boxes, you decide whether or not there's an object in this, in these bounding boxes, and then you use that information, calculate the error, and then you kind of refine these bounding boxes until they kind of align with where, the object is. So the first step is to initialize, the region proposals, and then you kind of have this retrain, relocalize loop where you train, see what the error is, refine the bounding boxes, and then train again. So it's kind of this continuous loop until you converge or the error doesn't, go down as fast as you like. So the challenges here is that it's very sensitive to initializations. So depending on the bounding boxes you provide, it may give you wildly different solutions. So the initial set of bounding boxes that you provide are very important when training such an object detection system. And they also tend to overfit, where if you don't, if your, quality of the bounding boxes is very inaccurate, then it'll try to fit a model based on, those kind of windows. And those are actually locked in place when you're training. So actually, at least at the very beginning. So if you have very poor bounding boxes to begin with, and it's trying to refine those very poor quality bounding boxes, then that may tend to overfit and you may have a poor quality system. So those are things to keep in mind. So here's a quick summary in terms of, I wanted to talk about the very seminal work by Bill and Videldi from 2016 CVPR, which actually introduced this kind of system. So you use a pre-trained convolutional neural network. In this case, they use VGG16 backbone that was trained on the ImageNet database. And you actually lock so you're using that as a feature extractor. So you're not actually, you're actually keeping the feature extractor part of this locked, and then you add additional convolutional layers on top of this, and that is what is actually trained. So you start off with a pre-trained CNN, and then you change the last pooling layer to something which is called spatial pyramid pooling. So I'll talk about that in a little bit. But essentially what it's used for is bounding boxes at different sizes. And usually with convolutional neural networks, the image size is fixed, whether if it's 224 by 224 or 256 by 256. So this spatial pyramid pooling allows a dynamic, input image size. So usually bounding boxes are different sizes. So this allows you to take that, image size that is dynamic and to convert it into a fixed set of features that you can tack a fully connected layer on top to be able to do some training. And I'll talk about what that is in a little bit. So what you do at the very beginning is you have a pre-trained CNN, and you also have region proposals where, a bounding boxes of potential objects would be. So that is computed offline. And I'll talk about some, methods to actually compute those, but those are actually computed offline with a separate algorithm that will tell you where potentially, objects of any kind could be. And then after you have these region proposals, and then you have this feature extractor, what you do is you take these region proposals, and then you project these onto the feature space for the once you pass it through the feature extractor, and then you run it through a spatial pyramid pooling to give you a fixed feature size. And then it splits off into two separate branches. You have a recognition branch that'll tell you whether or not there is an object of this class in the image, and a detection branch that'll actually tell you where in the image this object exists, if it does exist. So once you have these two branches, and then you actually pool them together to give you a final kind of decision whether or not there is an actual object that exists in the image. And also remember that the ground truth are image level labels. So all we have available is just whether or not there is an object that exists in this image. So we have to create a loss function that'll work on that ground truth with using the bounding boxes that we take into account. So that's what this pooling here is for. So that's that we can create a very clever loss function that operates on these image level labels to actually train this object detection system to be able to hopefully make it as accurate as a strongly supervised counterpart. So how do we get region proposals? There's many different ways. One way is to naively just take sliding windows to kind of slide it across the image, and each window is a potential bounding box that you send to this system, and then you can decide whether or not there is an object that exists or not. But there's a lot of problems here. For one, there are simply too many. You also have to take into account, how much do you slide over, the size of the boxes. So there's a lot of hyperparameters here that may become unwieldy when you want to use sliding windows. But there are two other algorithms that are used, predominantly in practice if you want to do kind of weakly supervised object detection. There's something which is called selective search. So what that does is that it looks for regions of uniform color and shape. So it starts off from very coarse representation, very fine representation, such as you see on the left, and then it starts merging, regions together based on similar shape and color, to the point where it progressively becomes something like this. So then once you have regions like this, you put a bounding box along each of these regions, and those are the actual region proposals that you send to the algorithm. And there's another algorithm called edge boxes, which I'm not too familiar with. I'll just leave it there in case you want to look at it, but selective search is the one that I'm most familiar with. Also, because you have a wide variety of overlap, you definitely want to apply something called non-maximum suppression that'll remove a lot of these overlapping bounding boxes, so that you get just one consolidated bounding box within a cluster of very similar ones that are close to each other. So just a quick overview of spatial pyramid pooling. So what's happening here is this is the output of a convolutional network before you do any fully connected. So this is before the flatten operation. So you have a bunch of convolutional neural nets, and then this is the very last layer before you put it through fully connected heads to do classification. So the point of this here is that it's able to produce a fixed feature size, so that it'll ignore the input bounding box size taken into account. Usually with image classification, you assume that the image size is fixed. If it's 224 by 224 or 256 by 256, whatever. This allows you to input in bounding boxes of any size, and then the output will be a fixed feature size that you can tack on to fully connected layers on top, so that you are ignoring kind of the size requirements that is required when you're actually doing an image classification. So how it works is you take a look at the output feature map, and what you do is you start decomposing it into multiple grids. So the first level here is you basically do pooling on the entire output map. So for all intents, for the sake of this example, there, let's say the output, we have 256 filters of a known size. So the first level, for each filter, you do pooling on the entire spatial domain. So let's say, for example, this is 32 by 32, and you do max pooling. So the first level, you do max pooling on the entire 32 by 32 sub image, and then you do it for all the filters. And then the next part is we decompose this into quarters, and then you take the max pooling of each quarter, and that now gives you 5 features. So 1 feature for here, and then 5 features for here. And then the next level on top of that is you decompose it again, but in this case, you have like a 4x4 grid or 16 by 16. So each cell gets split up into 4 other cells, and you do that for as many times as you want. In this case, we are just doing it 3 times. So you'll do max pooling of each, and then you stack all these together to give you your final feature vector. So in this case, we'll have a 21 element feature vector for this particular example. So you stack them all together, you concatenate them all together, and that gives you a feature size of 21 that you feed into a fully connected layer to do the actual classification. So this was their way of being able to do the classification on images where the size is unknown, because you're at the mercy of the region proposals. So this is their way of combating the fixed size. You don't have to resize anything anymore, especially if you want to keep the aspect ratio of images, and especially if it's small. So this is their way of combating the variable size of the bounding boxes that you're putting in. So if you recall, we're using region proposals that tell us what bounding boxes that potentially have objects in them. So what you're doing here is you have bounding boxes, and then what you have to do is you have to identify the features that correspond to the bounding box. So what you're doing here is you're doing what's known as a region of interest, or ROI projection. So this is a pretty good example. So let's say my region proposal was this green box of a cat, and I want to identify whether or not there's a cat in this image. So you put this, what you do is you put the entire image through your feature extractor, and then now you're left with a kind of a reduced it's a bunch of feature filters that are, let's say, of size 20 by 15. So usually when you have a bunch of convolutional operations and max pooling operations, you're reducing the image size down to, in this case, let's say it was 20 by 15 after you run it through a series of filters. And let's say there are 512 filters altogether. So what you're doing here is you have to figure out the receptive field that would map to this particular space. Really, all you do is you take the bounding box coordinates and just divide by the receptive field size. So in this case, 640 divided by 20 is 32, and 480 divided by 15 is also, I think, 32. Yeah, so there's a scale factor of 32. So you take the image coordinates divided by 32, and this gives you the equivalent coordinates in feature space. But notice here that they don't necessarily align to the coordinates here. So what you have to do is you have to snap it to the closest coordinate in this space. So then once you have this bounding box, then you do your spatial pyramid pooling on this to give you your fixed feature representation. So that's how you take your proposal and bring it to feature space, the equivalent bounding box in feature space, snap it to these grid cells, because when you're doing when you're figuring out the equivalent coordinates in feature space, it may not give you an integer number. So you'll have to snap it to these, snap it to the nearest cell location, and then you do SPP, on that final region. So once you isolate out the region that I just talked about, you perform spatial pyramid pooling. And then once you have, these spatially pyramid pooled features, you split off into 2 branches, as I talked about. The first branch is, your classification and detection, right? So we've got 2 fully connected layers that split off. So you have so once you have spatial pyramid pooling, you run it through a fully connected layer, which is called FC6, and then you have another one, FC7, that finally gets split off into 2 branches. You have a classification head, which tells you whether there is an object of the kind that you're looking for in the image, and a detection head that will isolate where the actual object is located. So the goal of this classification head is to provide a C-dimensional vector of class scores, whether or not there is a presence of each object that is inside the image. So if there are C classes, we get a C vector. And then you also have a detection kind of head that's also mapped to a C-dimensional vector. And then they're both applied with a softmax. So you can think of classification as whether or not there is an existence of that particular object. And there is a detection head that's slightly different where it's based on the bounding box that you provided. So the detection head here tells me that if I am provided a bounding box, that is presented to the system, how likely is this particular bounding box suitable to represent what object I'm looking for? So that's what the detection head is for. So this is a quick block diagram of the whole system here. So you've got your region proposals. This is the last pooling layer for VGZ16. Run it through spatial pyramid pooling, attach it fully connected, and then another one. And then you split this off into two branches. You have a classification head, you have a detection head. And then what we see here is this is what happens if we want to eventually train the system. So you actually take these two outputs and you actually do a multiplication, like an element-wise multiplication together, so that together they give you kind of the information of both, whether or not there is an object that exists, as well as how likely the bounding box that was provided is the best way to represent that class. And then there's a summation operator here, which I'll talk about in the next slide. That'll give you your kind of final class scores. So let's say we've got our proposals. So let's say for an image, we have a bunch of region proposals. And we want to evaluate whether each of these proposals has the object or not. So when you do a forward pass of the system, what's going to happen is you're going to have actually two matrices for both branches. So the classification branch will have a two-dimensional matrix where each row tells you the scores for that particular class. So the rows are for the class, and the columns are for each proposal. So what you do here is if you want to get kind of the final kind of class scores for for each proposal, you just multiply these, two matrices together. And then we're going to call this matrix X, superscript R, where this tells you that for each column or for each proposal, how suitable that proposal is to represent the object that you're actually looking for. So, so once we have this matrix, in the end, we only have image level labels. So what you need to do here is you have to convert this into some global representation so you can actually do your training. So what you do here is we have a C by R matrix. If you want to consolidate all this information together, all you have to do is for each row, just sum over all the columns. So you get a C-dimensional vector that actually will tell you what the likelihood is that the object of interest exists in that image over all the proposals that you have. So this is the vector that you use to actually train your loss function. So you have a consequence of the region proposals that you're using at inference time, but for training, you have to have this additional kind of loss function that's tacked on top that operates on the global labels to actually tell you whether or not you're actually training the system correctly. So what's nice about this is that each row by themselves sums to 1 because you are representing the likelihood of every kind of bounding box over every class that you're looking at. So each row by themselves will sum to 1, but each column does not necessarily have to, because you want to detect whether or not there's multiple objects of different kinds in the image. So quickly, this is the loss function. You have some so we're using L2 regularization. So you're just basically just summing over kind of the weights squared. And then this is basically just your standard binary cross entropy, where what you have here is N is the total number of images that you have, C is the total number of classes, W or your network weights, and then Y sub Ki is the ground truth. So this tells you whether or not the object of class K exists in image I. So if you actually work this out, this actually works out to standard kind of cross entropy, where this is the probability of the class existing in the image, given the features from the spatial pyramid pooling, divided by the weight. So if you actually work this out in your head, so it's actually log of x plus 1 minus log. So this actually works out if you actually actually sit down and work out the math. But this is basically just your standard cross entropy, whether detecting whether or not there is an object or not, in the actual image. I'm not going to be able to go through the research. So I'm just going to talk about results and then I'll stop it. I'll talk about maybe the research another time, but I'm going to finish this off. So we have something which is called a spatial regularizer, where the loss function is optimized for just taking a look at image level labels, but it doesn't guarantee kind of spatial smoothness or the way the bounding boxes would naturally occur in the image. Let's say if an object were to move from one position to another, we also want to reflect that motion smoothly. But because we don't have that in place, the way that the kind of object may move, because we're at the mercy of the bounding boxes, that motion may not be adequately captured. So we have this spatial regularizer here that will help us kind of enforce smoothness when objects are moving in between scenes. So specifically, if a region proposal contains a high score, then neighboring proposals that have high overlap with this particular region proposal should also have high scores too. We want to make sure that similar region proposals that overlap a very good bounding box should also reflect very high scores as well. So we actually don't have access to any ground truth bounding boxes, right? So this actually complicates things a little further. So what you need to do here is you need to implement some regularization strategy to penalize whether feature vectors do not agree with the main overlapping bounding box. So what you do here is you take a look at the ground truth class that is available for the image, as well as the bounding box that contain the best overlap of that class inside the actual image. And then you grab neighboring bounding boxes around this best scoring one that have at least a 60% intersection over union with this highest scoring bounding box. So what we're saying here is, given an image that does indeed contain class K, given that matrix that we talked about, so there's that XR matrix that gives you the list of scores for all the region proposals, what you want to do is figure out which class. So what you want to do is you want to find the proposal with the highest score. So what you're doing is, for the ground truth row, you want to look along the columns and choose the value that was the highest, which tells you that this is the most confident bounding box that contains that particular object of that given score. And then what you'll do is you'll take the score and compute this with, and compare the score with all the scores of the overlapping proposals, and you want to make sure that this distance is as small as possible. And if that's small, then that means that you are properly enforcing kind of this neighborhood consistency that we're talking about. So this is just very briefly what this is. So N sub K plus is the total number of images that contain class K. You also have R hat, which is the number of region proposals that contain the class, or that is, the number of neighboring proposals that are around this overlapping bounding box. And then you have this output score, phi of y k star I, which is the output score of the region proposal in that image that was the highest that represented that actual class. And then what you're doing here is you are computing kind of the similarity in feature space between this bounding box's features with the rest of the other features that overlap this bounding box. So you're just computing kind of the dot products between those and just accumulating all those and finding the average distance. So you add this regularizer on top of the loss function, as well as the other loss that I talked about. So when you're training, you have just one image, and the mini batch contains all the region proposals for that one image. So at training time, you just have the one image, you have all these region proposals, and then you are training kind of one image at a time, but the number of region proposals will change depending on what image you look at. And then at inference time, you don't have, so all you're doing is you have an object detection system now that has hopefully, understood what it is, for these bounding boxes of, where the images, where the objects are. So at inference time, what we're doing here is to accommodate for different scales, the image, the input image may be at different scales. What we want to do here is we're going to do inference 10 times. So the first time we'll take the image and resize it to different sizes, just to maintain the aspect ratio. So either the width or height has to be 480, 576, 688, and so on. And then you also flip the image horizontally so that you have 5 copies of the other 5 here to give you 10. And then you run it through the system 10 times. And then you have scores for each of these 10 images. You just simply average them, and that is the final result that you have. So here are some, sample results. So green means that the object was identified correctly. So there's some ground truth bounding boxes from the Pascal Visual Object Challenge database that we're using to see whether or not the system was quite accurate. So green means that we consider this a successful detection, and red means that you've either not, so something's wrong with it. So in this case, we see that there are 5 planes here, but the object detection system decided to group all these as to one object, mainly perhaps because the at training time, there could be a lack of kind of bounding boxes available, and also the objects here are quite grouped together. And in terms of here, we expected, the cat to fully encompass the cable, but it only isolated out the face. And I suppose that's that's a reasonable mistake because, cat faces that identify the cat are obviously distinctly, they're quite different from human faces. Then you also have this one here where we've identified kind of multiple sheep in a single bounding box, so that can fail too. Multiple objects, you also got a person. We would expect the bounding box to go over the entire person, but we've only isolated the face, and I suppose that the face is the most discerning thing about a human that you probably look at, so that's probably where it failed too. And the same thing for the dog. We expect the bounding box to encompass the entire body, but for us personally, we take a look at the face to see, we look at the face first to see what kind of dog it is versus the rest of the body. So these are reasonable kind of mistakes. But at least it identified where it actually was, in the actual image. So I don't have time to go through the research, but I'm just going to jump right to the end. If you want, I'll make these slides available for you to take a look at the research, but I don't have time to go through that. But so I'm going to conclude this talk. I gave a brief introduction to kind of WSOD, and hopefully I give you enough to get started to allow you to study this further if you like. I also presented, the work by Bill and Videldi. It's the seminal work where everything is based off of that. You've also got very clear advantages and disadvantages with WSOD. So the advantages include getting, trading data in a much easier way, just deciding whether or not there's an object inside the image versus bounding boxes. Technically, it's technically faster training time because you're not training a full convolutional network. Like you're freezing half of it to do a feature extraction, and then there's just a few fully connected layers that are connected on top that you're training to actually do the localization. This is still a widely unsolved problem, and each year there's more and more papers out there that are actually continuing to address this problem, mainly because it inherently solves the problem of big data, right? So if you have, let's say, a lot of images that are unlabeled, it's better to have just a single kind of global label or global labels on an image than having to have bounding boxes that are isolating out the objects. So you're able to get training data more quickly. And even though there are some problems with it, it's still used in many areas, especially medical diagnosis with very high resolution images. You don't want a radiologist to sit there and kind of do bounding boxes on a lot of cancerous cells. So it's better to just tell them, ask them to tell us whether or not there's something wrong with the image, and then we figure it out ourselves later. It's also used in automated image labeling, where you can use this to identify potential objects in an image, and then you can correct these after and provide this as kind of a ground truth to a user if they're interested. So there are some kind of image labeling companies out there that actually use WSOD as a way of speeding up the process to give you ground truth data in a strongly supervised way. And obviously scene understanding and object detection obviously is where it's being used as well. And with that, I yield my time. Thank you very much, and I'm open for questions.
Awesome. Well, thank you so much for that really informative and super interesting presentation. I'm definitely going to go look at your slides after this. I feel like I have like so much content that I'm definitely going to go back and like look at afterwards as well. So again, you guys, if you have questions, put them in the chat, or you can use the raise hand function and we will unmute you.
I will stop.
So kind of while waiting for people to ask questions. So I have I'm kind of curious about something. So I know earlier you had mentioned that WSOD is like a widely unresolved problem, and there's like a lot of research happening in the field. And then you also talked about one specific paper by how do you pronounce the last name? Bilal.
Yeah, Bill and Videldi. Yeah, sure.
Yeah. And what other papers would you recommend that we kind of look at if we're interested in this? Are there any papers that, take a different sort of like approach that you think would be good to compare for reference?
Yeah, sure. So, okay. So I should probably share my screen then. I naively turn it off. Okay. So I'll just talk about that now then, since we're here. Okay. So there were 3 papers I actually wanted to talk about. They didn't have the time. So there's one which is called cross domain, where the objective is having, a bunch of images that are not only weakly labeled, but or of a completely different domain. So for example, the goal here is you have images that are of artificial nature, so, such as clip art or watercolor or comic. And for here, we label these. And can we not only train an object detection system to find these objects, but can we train it in images or videos that we've not seen before, such as real life footage? So this is from CPR 2018, where they do what's called cross-domain training, where they have data from one domain, and can we figure out ways to understand what objects are from this domain and apply to a completely different domain altogether. So this is one thing that I actually found quite interesting. And then there's another one by, let me see here. There's also one by Towards Precise End-to-End WSOD by Yang, where they completely get rid of the region proposals. So instead of having kind of region proposals that are offline that you're using, can we train an end-to-end system that will learn the actual proposals that are required to give you the objects that you need? So this was actually proposed as well. And then there was another paper by, let's see here, by NeurIPS 2020, where they actually address some of the challenges in WSODs, such as, identifying. So for this one here, you have a bounding box that kind of labels all the sheep, but we actually want to identify each sheep by itself. So this paper actually addresses fixing some of those challenges to be able to identify individual objects better. So those are the three that I look at, and they're part of my slide deck.
Awesome. Yeah, that's super helpful.
So I actually have a question. Sorry to interrupt.
Yeah, sorry.
So maybe naive, but is there overlap with like other data types? For example, maybe I've got some audio and I know that there's a sound present in it, but I don't know where exactly in the audio clip it is. Like, is that a completely different problem domain, or is there some overlap?
It might be related, but with audio files, you usually apply, the Fourier transform or the FFT or the spectrogram, and then you can collectively. So with the Fourier transform, because it doesn't take, time into account, it'll give you kind of the, frequency distribution of your data throughout the entire audio. So I think you could use just the Fourier transform to tell you, that there's a noise or some sound that exists, but you actually don't know where exactly it is. And then you can use either, short time Fourier transform or spectrograms or wavelets to tell you where exactly it would be. So I think you could do that, but I've never actually seen kind of a neural network approach. That's something interesting to explore, especially because, Fourier transform and, short time Fourier transform, those are handcrafted features. So if we could train a neural network to tell us, where exactly it is by just, presenting kind of examples, of audio clips, and that might be something interesting to explore.
Cool, thank you.
I have a kind of like a sort of related question. So I know you kind of talked about, the paper by Villan and Vidaldi, and also you talked about different kind of like approaches, like cross-domain WSOD. Do we ever run into the problem of like catastrophic forgetting, especially when we kind of like earlier you talked about having like a pre-trained convolutional neural network on like ImageNet and also like training on different data sets? Is that like a problem in the WSOD kind of like
field? Yeah, definitely. So for you can tell here that with ImageNet, it's trained a very natural images. If you wanted to do it on a completely different domain, such as, let's say, medical images, the feature space that you'll learn from, it's a source of debate. Like, we're split down the middle here, but the pre-trained CNN that you get from ImageNet being applied to medical images may not be the most suitable, mainly because, well, you have completely different objects, completely different color representations, completely different compositions. So when we have kind of a pre-trained net that's frozen, that the features that are represented with that may not be the most suitable, and that could be a candidate of not properly learning kind of the feature space. So it's definitely possible to open it up end to end, where you can actually, unfreeze the network and maybe over time, grab some examples, see if, the classification system detected it properly. And if so, then you don't have to worry about it. But if not, then you can use that and kind of fine tune the other layers so that it can take these features into account. But yeah, it's a definite problem. I'd say that, and the solution is to just open up the network and not make it pre-trained anymore. Fine tune it based on the examples that you have, and that way it will be able to fold in the information that you presented to it at test time back into the weight, so that you can still incorporate that information.
Awesome. I think that's really interesting. Yeah, and it's also like a really cool kind of like active portion of research. So we know that
Yeah.
you have like a hard stop. So I'm gonna end with like one last
Oh,
question.
that's okay. We still
So
got 10 minutes,
in
but sure.
terms of oh, okay. So I guess like in terms of I know you talked about the papers earlier, and then you also talked about sort of like different areas that you can kind of study as like preliminaries in the
Sure.
beginning part of your talk. But
Yeah.
for mentees and mentors and just like anybody else who's watching this, and they,
Hmm.
for example, like if they want to start a project or like work on a
Hmm.
project in this field, do you have any like recommended data sets that they can look at? And in addition to that, do you have any like notebooks or like GitHub repos that you think would be cool to
Okay.
like
Yep.
refer to?
Cool. Yeah, so the one data set you definitely want to look at is the Pascal Visual Object Challenge data set, or the Pascal VOC. So it has bounding boxes and image labels for each object, for all the objects in the image. So if you wanted to do WSOD, all you have to do is just throw away the bounding box, definitions, and just leave the image level labels. But with the bounding boxes, you have ground truths. You can assess the performance, but you can start off with the Pascal VOC and just remove information that you don't need to simulate a weakly supervised system. So you can take a look at those. The data set is updated every year. Like the one that I presented was from 2010. That's the version of the data set, but it keeps getting updated every year. So that's a data set to take a look at, and it's actively being updated, and it's there's a lot of contributions to it. In terms of resources, so a lot of the information that I pulled was from a tutorial by Hakan Billen himself. So it's from ECCV 2020. So let me just, where is it? Let me go find the, there. Oh, no, that's it. Here it is. So if you take a look at the European Conference in Computer Vision 2020, there was a whole kind of seminar on it over 2 days where they actually talk about weakly supervised object detection. So they talk about this as well as the latest state-of-the-art research and the challenges. So they go into much more depth than I do. So this is kind of a whirlwind tour about it. But if you check out the tutorial by Hakan Billen from ECCV, there's a whole seminar about it, as well as in terms of GitHub repos, he actually has a implementation of this, but it's using MATLAB. So there have been contributions in TensorFlow and PyTorch that have translated this to those ecosystems to be able for study. So I think it's an interesting problem, mainly because it circumvents kind of the big data problem that we're talking about, where you have to find bounding boxes and image labels, but then if you want to collect your own data, it's much easier to kind of go through yourself and say, yes, this is a sheep, this is a dog, and so on. So you're actually creating your own training data very simply, and definitely if you want to use web scraping too, and being able to collect those is a much easier way of collecting data than to having to go through all the bounding boxes and putting them in yourself. So start with the tutorial, take a look at the data set as well. There is an implementation of this. There's several implementations of this online if you want to get started. And then once you have that going, maybe start collecting some of your own data and just labeling that very simply with global labels, and see if you can train your own detection system.
Awesome. Thanks, Ray.
No problem.
So I think I have like one last question. So I
Yeah,
mean,
go for it. We got time. We got time.
About like region proposals and like how we get that. I think you talked about a couple of methods, if I understood correctly, such as like sliding windows and selection search and edge boxes. So when would we use, or why would we use selection search over edge box, or like how would we know which one to use?
Yeah, so they both have advantages, but it's pretty much split down the middle in terms of what to use. But in terms of ease of implementation and availability, selective search is much more prevalent, especially if you take a look at kind of image processing toolkits such as OpenCV or Scikit-Image. Like, they have selective search already there. Edge boxes, from what I know, is slightly more complicated, but it's actually much more efficient to generate. So it's the ease of availability versus computational complexity and efficiency. So it's actually split down the middle in terms of what to use, but either one is perfectly acceptable. They work roughly the same way, but they use slightly different criteria to get your region proposals. But you start with either one. There's no clear definitive winner. But the answer to this is to simply try both and see which one performs better. But usually selective search is the one that is chosen the most often, mainly because it's mostly available and it's easier to understand.